One final example of being able to find max and min points, and this is one where it's extremely important for us to be able to not rely on the graph, is going to be this x squared y squared minus 8x plus y all over xy. And let me show you what the graph of this looks like. Because if we were just use the graph of this thing, then unfortunately, this is what we would end up with. And unfortunately from the graph, even by rotating it, it's very difficult to see any max, min, or saddle points. So that's why we have to rely on the analytic calculus to be able to help us out. Now fortunately, this one's not too difficult. All right, so let's go ahead and start by rewriting the function. And we can start by using this trick. Remember the algebra trick that if you divide by a monomial term, you can just break it up into 3 separate monomials. And so f of xy in its new form is going to be xy minus 8y to the minus 1 plus x to the minus 1. Right? And I did that because obviously we have to set it up for differentiation. F sub x, easy to find, y minus x to the minus 2, otherwise known as y minus 1 over x squared, and that's going to be equal to 0. And then for fy, again, that's pretty easy too. That's going to be x plus 8y to the minus 2. Or, another way to write that would be x plus 8 over y squared equals 0. And of course the question is, well, how do we solve this? Okay, well, what we can do is we can use substitution this time. All right, in the last 2 examples we were able to factor, and it just worked out really nicely to be able to find those critical values. This time we can rewrite f sub x equals 0 as y equals 1 minus x squared, and then we can just substitute that back in. So by substitution we get x plus 8 over 1 over x squared equals 0. A little bit of algebra later, x plus 8 x to the 4th equals 0. All right? And even though you might not like that polynomial equation, number 1, it's a polynomial. Number 2, it's very nice and factorable. All right? And so finally we get 2 solutions. X is equal to 0. That's an easy one. And then 1 plus 8x cubed equals 0 is going to yield this solution. So we're going to subtract 1, divide by 8. So we get x cubed equals negative 1/8. And if we take the cube root of both sides, fortunately, 8's a perfect cube, 1's a perfect cube, and we end up with x equal minus 1/2. So that's really nice. Recall that 0 is not in the domain of the original function, right? And that makes sense for us to get 0 as a critical value, because you might recall that a critical value is any value that makes the derivative 0, or it's a value to where the derivative is undefined at that point. All right, so this is not in the domain of f, so we just ignore it. Right? Also recall that we said that y is equal to 1 over x squared, and so we can solve for y readily. So y equals 1 over negative 1/2 squared, and then you can throw that right into your calculator or do it by hand. Either way, you're going to get 4. All right. So now we know that the point that we're looking at is minus 1/2, 4. Let's see what type of point we're looking at. To be able to do that, we need fxx. fxx is easy. That's just going to be a positive 2x to the minus 3. We need fyy, and fyy is going to be negative 16y to the minus 3. And even easier is fxy. All right, so fxy, Notice that that just becomes 1. When we take the derivative of y, that goes to 0. So fxy is equal to 1. Right? Remember that d is fxx, fyy, minus fxy squared. And so d in this case can be written in one of two ways. 2x minus 3, negative 16y minus 3, minus 1 squared. Or, a little bit easier, negative 32 over x cubed y cubed minus 1. Fortunately, we only have one value to concern ourselves with, and that one value is going to be negative 1/2 4. And so d at negative 1/2 4 is going to be equal to negative 32 over negative 1/2 cube 4 cubed minus 1. All right, and I think that's going to work out pretty nicely because the denominator is going to be negative 8 times 60, negative 1/8 times 64. So that should be negative 8. This should be negative 32 minus 1. Verify this though when you can. That should be 4 minus 1, which is 3, which is greater than 0. All right, so that means that we're either going to have a max or a min. So it's up to us to see which one we have. So we go back to fxx at the point negative 1/2 4. And 2x to the minus 3. So that's 2 times minus 1/2 to the minus 3 power. All right, just substituting right in here. That's going to be negative 8 times 2. So that's negative 16, which is clearly less than 0. And so what we have is we have a max. And finally, let's just substitute the original function or the original value back into the original function. So f at minus 1/2 4 is going to be equal to, I forgot what the original function was so long ago, x squared y squared. So that's going to be negative 1/2 squared, 4 squared. And again, I forgot. 8x plus y, so that's minus 8 times negative 1/2 plus y, which is 4, all over negative 1/2 times 4. All right, so the denominator is negative 2. Numerator, 16 times divided by 4 is 4, plus 4 plus 4. All right, so it looks like we're going to end up with a negative 6 for D, or for fxx. All right. And fortunately, that's going to be good for us. All right, so that way we can be done with this. So our final answer is going to be that there is a local max at the point negative 1/2 4 negative 6. All right, and again, the good news for this problem, or the whole use of this, is because when we looked at that graph using GeoGebra, unfortunately, or whatever program we use, it was just pretty difficult for us to figure out any max, min, or saddle points. All right, so hopefully these 3 examples illustrate how to go through and find max, min, saddles of our functions in 3 dimensions. Now we're going to start applying those to some real-world types of problems.